Hello, this presentation today will be on the topic of labels for AI as part of the medical imaging data track of the SIIM Clinical Data Informatica series. My name is Paul He, and I'm a musculoskeletal radiologist at the University of Maryland, where I also direct the University of Maryland Medical Intelligent Imaging Center, a new AI research center to be launched in early 2022. I have the following disclosures, none of which are relevant to this talk. Today's presentation will have 4 learning objectives. The first, to summarize the role of imaging labels for radiology AI. The second, to review key developments in creating labeled radiology imaging data. The third, to identify the different types of labels for medical imaging data. And fourth, to review challenges in labeling radiology imaging data. Let's begin by discussing the role of imaging labels in radiology AI. As many of us know, AI has received tremendous attention and excitement across multiple fields, including healthcare and radiology. What has been critical to this is something called deep learning. Traditional machine learning requires an engineer to specifically define features to be extracted for classification of an image. Deep learning gets rid of this step, allowing for feature extraction and classification to occur without explicit programming. The predominant algorithm type that allows for this is the convolutional neural network, which works at a high level like this. First, you have an input layer where an image or data of interest is inputted. Next, you have a hidden layer of feature detectors which identifies low-level features, things like lines, curves, edges. These are subsequently combined in later layers to increasingly complex features such as eyes and noses in this example, until you start seeing something like a face. And ultimately, there can be a final output layer of a decision. In this case, it might be what is the identity of the face that was inputted. One way to conceptualize imaging data for radiology AI is that they're sort of like flashcards. You might have an image on one side and the label on the other. And you need to train a model with both of these things to have them learn, similar to how we might have learned shapes when we were children. Now that we've talked about the role of imaging labels, we'll review some of the key developments in medical imaging labeling over the past few years. Deep learning requires massive amounts of data on the scale of hundreds of thousands of images. Perhaps the most meaningful contribution in data for deep learning is the ImageNet dataset. ImageNet was originally comprised of 1.2 million images with over 1,000 object classes and was created through the use of Amazon Mechanical Turk, which had people all over the world hand-label images from the internet. Starting in 2010, ImageNet hosted a competition called the ImageNet Large-Scale Visual Recognition Challenge to develop algorithms to classify this dataset. In 2011, the best performing model had a 26% error rate. But in 2012, this dropped to 16.4% through the use of a new type of algorithm called AlexNet, a convolutional neural network, and is a type of algorithm predominantly used today. And in subsequent years, the best performing algorithms have all been CNNs with steadily decreasing error rates. And I point out that all of these are what we now know as deep learning. One key concept for radiology is transfer learning, where one can take a CNN trained on one large set of images as a starting point and fine-tune them on smaller sets of images like in radiology. For example, we might have a neural network pre-trained on ImageNet, and then we fine-tune it on chest radiographs, on head CTs, or on renal ultrasounds. This is particularly useful because curating millions of images in radiology is difficult, and transfer learning can reduce the number of images needed to train a high-performing algorithm. Radiology had its first mini ImageNet-style moment of sorts in 2017 when the NIH released over 100,000 chest x-rays for the development of deep learning models. And since then, over the past 5 years, we've seen a surge in publicly available chest x-ray datasets with increasing numbers. For example, in 2016, the largest dataset was about 7,500, followed in 2017 with 112,000 by the NIH, and then in 2019, with 220,000 and 370,000 x-rays respectively from Stanford and MIT. These efforts have also been augmented by multi-institutional efforts led by radiology societies like SIIM and the RSNA to crowdsource high-quality labeled data, which continue occurring on an annual basis for the various society meetings. Now that we've talked about developments in medical imaging labeling, let's review different types of medical imaging labels. There are 3 basic types of deep learning models, each of which will require its own type of label. The first is an image classifier, which asks a model to classify an image into one of 2 or more categories. The second is an object detector, which asks the model to identify specific objects in an image. And the third is a segmentation model, which asks a model to identify specific objects or items and outline that item of interest. Classifiers will require an image-level label for the category of interest. For example, yes or no for dog or pneumonia. This is the simplest kind of label and does not require any annotation of the image pixels themselves. Object detectors will require bounding boxes placed on the images directly along with a category label. This does require radiologists or other annotators to work directly with the images. And finally, segmentation models will require pixel-level segmentations with manual outlines of objects or items of interest, along with the category label. Below are some examples of annotations in radiology. On the left, we can see bounding boxes around lung opacities representing pneumonia, and on the right are segmentations of a right upper lobe pneumothorax and accompanying chest tube. Now that we know about the types of medical imaging labels, we'll move on to discussing some of the challenges in actually labeling these data. We'll review the following 4 challenges: accuracy of labels, ground truth definitions, time required for labeling, and bias that may be present in images. The first challenge is accuracy of data. We'll recall that in 2017, the NIH released the first large chest X-ray dataset with over 100,000 images for deep learning model development. And supposedly this dataset had 112,000 frontal chest X-rays, which seems like an easy enough thing to confirm based on DICOM metadata. But when we look at the images themselves, we can see that there are numerous non-frontal chest X-rays, namely lateral chest X-rays, along with some images that aren't even of the chest, including the abdomen. And so all of this is to say that metadata is not 100% accurate, and there will likely always be some error when using baseline data using metadata. When we look beyond simple imaging metadata and into accuracy of disease labels, the problem does seem worse. In this paper by Luke and Rayner, an evaluation of NIH chest X-ray 14 labels showed that the images were frequently incorrect, with positive predictive value between 10 and 30% lower than those reported by the original dataset. And so accuracy of data labels is an ever-present challenge. A second challenge related to accuracy of labels is the definition of ground truth. These can vary from radiology report to radiologist review, either a single radiologist or a panel of them, to review by other specialists like surgeons, and even surgical or pathology confirmation of a particular disease. I will note that this list is not exhaustive, and one can imagine multiple possible definitions of ground truth for one disease. For example, pneumonia on a chest X-ray could be defined by the radiology report, or by review of the images by a group of radiologists, or perhaps by correlation of the patient's clinical course to confirm if they indeed had pneumonia. One common concept in radiology is rad path correlation, where pathology analysis of tissue obtained from biopsy or surgery is often considered the gold standard. However, even for pathology, there can be disagreement between pathologists, and so the true gold standard can be more elusive than one may naturally assume. On a more practical level, data labeling is challenging because of the time required. For example, the RSNA PECT dataset required a year-long effort and thousands of radiologist hours and dozens of radiologists to annotate images for just one use case of PE detection. Imagine expanding this to every type of disease and dataset. Needless to say, this is one of the biggest bottlenecks in building high-quality radiology datasets for AI research. Given this demand for data labels and the time-consuming nature of the task, commercial companies have started to emerge to provide labeling as a service, such as Centaur Labs, which calls upon medical experts to provide up to 150,000 labels per day. The last challenge we'll talk about is the potential for bias in the images themselves. Recent studies have shown that imbalances in demographic representation in deep learning models can lead to biased algorithms. For example, in this chart, deep learning models were trained to identify pneumothorax on chest X-rays. When tested on images of males, models with more female representation, as noted on the x-axis, tended to perform worse on these male images, indicating sex-based bias in these algorithms. And just as concerning, in work by a team led by Dr. Judy Gichoya, deep learning models have recently been shown to identify race on medical images, ranging from chest X-rays to mammograms, which raises the possibility of racism being perpetuated in these models that might be reflected in the data sets that they came from. In conclusion, both the amount of data and quality of labels is foundational to the development of deep learning models in radiology. There are several different ways to label data depending on the type of AI model desired. And finally, although labeling medical images is challenging, innovative solutions have facilitated the creation of high-quality large data sets. Thank you for your time and attention, and we invite you to connect with us at SIIM via Twitter, the website, and to join us at our annual meeting and the SIIM conference.